G'day everyone, my name is Reuben. I'm the Managing Director of Packworks Construction Testing Equipment, and I welcome you all here today to our live stream on our YouTube. We're a company that operates within Australia and New Zealand. We sell a range of testing solutions for... G'day everyone, my name is Reuben. I'm the Managing Director of Packworks Construction Testing Equipment, and I welcome you all here today to our live stream on our YouTube. We're a company that operates within Australia and New Zealand. We sell a range of testing solutions for construction materials and projects. Those would include lab testing equipment for soils, aggregates, cement, concrete. It also includes ground penetrating radar, geotechnical instrumentation, metal NDT, and also concrete NDT. So this is the first of our live streams on YouTube, and what we're hoping to offer is a way of communicating with our customers and having a really good technical dialogue on important subjects. And so we're hoping to offer relevant technical presentations. And also, I think that it's also a good way that we could introduce new products and services to the market, and we could also tailor these for smaller audiences with more focused information for our customers. We're going to be looking to do these types of presentations probably once every 2 months into the future, and so look out online or in your email for invitations to these presentations. So let's get to today's presentation. Today's presentation is going to focus on AS 5100, and in particular it's going to focus on Section 8, which deals with the rehabilitation and strengthening of existing infrastructure. There are a number of NDTs mentioned within this code. Essentially what the code does is it recognises the important role that NDTs play in providing design inputs for the design of repair for projects. So for example, within cathodic protection, the role of half-cell potentials and resistivity is reasonably well known, although the techniques themselves are generally quite misunderstood. Within fibre reinforcing for concrete structures, NDTs have a role to play within the quality assurance and compliance for those particular structures. What the code actually does is it calls out a number of NDTs, and what we want to do is we want to look at each of those NDTs and really illustrate to our customers where they're applicable, how you would apply them to the structure, the suitability of those techniques, and then also just give you a general overview, because I think that a lot of these techniques are not extremely well understood, and the information within the code, while top quality, is not very detailed on the actual techniques. And so we're trying to provide our customers with a link between the code and the wealth of information that we have on these particular subjects. Now we're going to have plenty of time for questions, either during or after the presentation. You'll see to the right that you've got your live chat, and then also we can pass those on to the presenter afterwards. Or if you want to, you could actually call up your local PCTE sales office, and they'll be able to answer any questions that you have. So presenting today's webinar, we have William Ward. He is our New South Wales and NDT sales manager. He's a mechatronics engineer. He's been with the company for about 6 years. He has a wealth of knowledge on the subjects that we're going to be presenting today. And so I'm really looking forward to the offering that he's got for us today. I'm going to stay online. I'm going to be moderating and providing some answers in the web chat, and also liaising with the presenter. And so I'd just like you to once again sit back and enjoy this presentation as we bring it to you live on the internet. Thank you very much.
And good afternoon, everyone. Thank you very much for attending our first presentation. I'm going to quickly get things set up, and we'll begin our main topic. So the topic we'll be discussing today is the non-destructive test mentioned in the new bridge code, AS 5100.8, Rehabilitation and Strengthening. Now, this is the new bridge code. It was released in April of this year, and it covers both the design of bridges and the section specifically concrete, steel, timber, and composite bridges. In that, they could be for road, rail, pedestrian, or cyclist. The particular section I've looked into today is AS 5100.8, which is the Rehabilitation and Strengthening section. And this looks at using non-destructive tests for things like assessment of load capacity and also design of the strengthening methods. This section was added in 2017. It's new. The big reason that was added was that if you're designing a new bridge, you'd have a very formalized method to look at your design and go off standard prescriptions. Whereas if you wanted to specify repair of a structure, you'd be caught using international standards or manufacturer specifications or different tools to an Australian standard. It specifically covers the rehabilitation or repair of a structure to bring it up to an intended service level, the extension of life of structures. So if it had a 50-year design life, it could look at extending that to 100 years and what remediation would be needed to do that. It also looks at strengthening, so increasing the live load the structure can carry and the load capacity. Finally, it also talks about widening. Now, PCTE's particular expertise is in non-destructive tests, particularly construction materials non-destructive tests. So that's going to be the focus of my presentation today. I'm going to look at a section fairly early on. So for a concrete structure, they define certain condition assessment options and also where they can be used. So the damage and deterioration can be evaluated using destructive and non-destructive tests. They can be used as inputs to a design, to a service life calculation, and they can also be used to make the structure safe before further investigation goes. Not made to use directly, but used to assess, is it safe to access this area? Finally, when they're used as a design input, they could be used to look at options for rehabilitation. So do you strengthen with carbon fibre or do you use some other form? And they can also look at the extent. So if you need to apply a cathodic protection system to improve the corrosion performance of that structure, how much is needed and where? And on the right, you can see a few of the tests that are mentioned. Some are destructive, some are non-destructive. So what I'll do is I'm going to break out some of the tests we're familiar with and go through each of them individually. Another section where these tests are mentioned is the inspection for cathodic protection, which makes very heavy reference back to the cathodic protection Australian standard, AS 2832.5. In this we see some crossover with the previous section in that cover meters are still relevant and other tools. There's also some very important design inputs to this method, such as resistivity mapping of a structure before cathodic protection. I want to quickly call out something I'm not going to be covering directly, but is another large component of AS 5100.8, and that is the testing and remediation of metal structures. Non-destructive testing for metal is quite a bit more standardized. So if you look at this screen, you can see the individual Australian standards which apply to particular points of testing that are called out in the standards. My personal experience is less on the metal side of things and more on the construction material sides of things, so I'll be talking in more detail on that side in a moment. Finally, another section where non-destructive testing is mentioned is the masonry area, and these are some of the same tests that are mentioned in the concrete area. It's applying the same tests to a different material. So specifically they call out ground penetrating radar, ultrasonic pulse velocity and impact echo. Ground penetrating radar as a location tool and a sort of geometry tool, and ultrasonic pulse velocity and impact echo as a defect and quality tool. When I get to these in the non-destructive testing section of the presentation, I'm going to call them out specifically where masonry has some differences. So, The test methods that I'm going to be covering during my presentation, I'm going to begin with ones that are inputs to other areas of, inputs to design first. Then I'm going to come and look at tools that look at the geometry and the way the structure is built. Then I'm going to look at ones that will assess the structure for damage or defects. And finally, I'm going to talk about some that look at strength. So we'll be covering the following test methods, and I'm going to go into more detail in a second. For each test method, I'm going to go through a pretty standard thing. I'm going to look at a quick extract from the standard that is what's listed there. These are usually quite short, very basic descriptions of here is a non-destructive test, here is what it can be used to evaluate, and it may be that they give you a relevant Australian or international standard to refer to. Then for each test, I'm going to look at the theory behind its operation. And finally, I'm going to give a bit of feedback and detail on where the standard recommends. Is that very suitable, somewhat suitable, or is that something better addressed by a really experienced expert provider of the service, or perhaps needs a little bit more thought, or it is going to be not a straightforward application of this method. As a bit of quick background before we begin, I want to talk for 1 minute on corrosion of steel in concrete. So, corrosion of steel in concrete is caused by a corrosion cell where there are anodic and cathodic areas inside that concrete. And for corrosion to occur, you need certain conditions to be present at the level of that steel. There needs to be water and oxygen, carbon dioxide, to allow the corrosion reactions to occur. And there needs to be something that breaks down the passive layer of steel in concrete. When you place steel in a very basic environment like concrete, it forms a protective layer of oxide, and this needs to break down. Corrosion can occur. And typically this is going to be in marine environments, ingress of chlorides from salt water or similar, or it's going to be in areas away from the ocean, or in carbon dioxide rich areas such as road tunnels. It may be that carbonation is the aggressive chemical coming in. This is a real 5-second overview. It's just important to understand that this is what we're mapping when we talk about some of the non-destructive tests. So, the section of the standard that discusses chloride and carbonation ingress, I've called out carbonation in particular because it's got a little quirk in that they specify that before design commences, before the consultant starts working with their client on design, they need to come to an agreement on the methods to do their carbonation testing. Additionally, they specify an Australian standard for chloride analysis, and they indicate that carbonation can in fact be used, and in fact shall be used on concrete surfaces to measure the depth of carbonation using the phenolphthalein method. So, how does this work? For carbonation, it's the ingress of carbon dioxide from the outside environment through the concrete. The ingress of carbon dioxide forms in a more acidic environment, and it's possible to track this by the acidification of that concrete using a phenolphthalein solution. To do that, samples are taken, they're fractured, and the indicator is applied to a fresh concrete surface. The key point here is this is a very well understood test method, but you need to agree with it as a consultant doing the design before you complete the testing. One example method would be Main Roads WA test 620.1. Now, the chlorides, they actually mention the Australian standard 1012.20.2. This doesn't specify how to establish a chloride profile, so that's chloride concentration with depth of concrete towards the reinforcing steel. It instead establishes how to measure chloride from a sample of concrete dust or other material. So, provided you're working that the chemical analysis is complete correctly, you're compliant to the standard. But to make use of the data, you'll want to establish a chloride profile, chloride with depth. So electrical continuity is also called out as part of the potential mapping section, and it's very, very important in the design and installation of cathodic protection. The Australian standard mentioned in this is AS 2832.5. So AS 2382.5 specifies that the design drawings of the structure be checked for continuity. If you don't have drawings, they will need to be use other tools. And also that the electrical resistance can be measured using either the potential difference or the electrical resistance on site. And the criteria for those are 2 ohm resistance or 1 millivolt resistance. When you are evaluating this, it's not as simple as getting the simplest multimeter possible and using that on site. It's important to get a good quality calibrated instrument, and usually to measure both the resistance and the voltages. So now we come into tools that are used to look at the layout of the structure. We've established what levels we might have chloride or carbonation, aggressive chemicals that can cause corrosion. And now let's talk about some of the tools that can be used to work out where the reinforcing, which is at risk of corrosion, is. So under concrete cover, it specifies the cover reinforcement size and position should be carried out, and that they can also use this information for current flow during corrosion to get some idea of how quickly corrosion is going to progress. And they also call out specifically the use of a cover meter, indicating it can be used to measure the depth of concrete cover, estimate the size of the reinforcing bars, and determine the location and orientation of the steel. They also give a criteria for performance of 1 millimeters at a cover depth of 25 millimeters, so that's 1 millimeter's uncertainty. The way that cover meters work is they're a magnetic pulse induction tool. All the information the cover meter has is how much magnetic signal is coming from reinforcing bars. To make use of that information, a bar diameter is entered into the system. This is one of the key criteria of a cover meter. And they're going to convert the information of signal strength plus bar diameter to a depth into the concrete. The precision defined of pulse induction cover meters is very good these days. You can easily achieve the 1 millimeter uncertainty at 25 mils, provided they're used correctly, taking into account the orientation of the bars, and they're set up with the right bar diameters. So, how's the cover meter going to perform according to standard? Location and orientation are going to work really well. They can find the bars, they can lock onto them, they can give information about their position. It's going to work extremely well for the depth of cover. The only thing better than a cover meter measurement for cover depth of reinforcing in concrete is physical inspection, physically drilling or chipping away and measuring. The bar diameter is an estimate. It says it in the standard, and that's true in the world too. It's critical to locate bars separate from other reinforcing, and then the cover meters will give a reasonable result, but it really should be confirmed by destructive testing. They did call out in another section of the standard it could be used to locate reinforcing before coring, where cores need to hit or miss the reinforcing. That works fairly well, but cover meters do have a depth limit. They're about 140 millimeters maximum depth penetration. So if you need to core deeper than that, it would be important to physically use other tools like ground penetrating radar. They're ideal for locating regions of insufficient cover. They're ideal for giving other depth inputs to design life calculations. So if you know the diffusion rates of chlorides, you don't know the current depth of steel, once you've got the two, you can form information there. Finally, I did call out congested reinforcement separately. If you have very closely spaced bars, say 100 millimeters diameter or less, it can start to become difficult to locate individual bars using a cover meter. The depth measurements can still be corrected and made useful, but the individual location starts to lose performance. This is more pronounced the deeper the reinforcing bars are into the concrete. So the next non-destructive method I want to talk about is ground penetrating radar. This is a very widely used test, and you can sort of see from the description here how many things it can be applied to. They specifically call out locating steel and other embedments, locating voids and delamination, looking at cracks, and some of these are going to perform better than the other. So whereas cover meters were a measurement technique, a ground penetrating radar system is a scanning technique. A pulse of electromagnetic energy, a radar pulse, is sent and received by the antenna, and this process is repeated as the antenna is moved across the concrete surface. This means it's going to be very sensitive to what electromagnetics are affected by, and it's going to provide a detailed picture. So you can see a sample reinforcing scan on the screen here, where they picked out individual reinforcing bars, and also be able to evaluate information such as the slab thickness and multiple layers of reinforcing. This is the real output from a ground penetrating radar. So if we then go and look at the stated performance of this information, we can see it's going to be better at some things than others. The reinforcing location is very clear, and the arrangement is very clear. Now, because the reinforcing bars are not displayed as a one-to-one representation, their size, their diameter is less clear. Some operators will use estimation techniques, but this does need to, again, be considered an estimation rather than a measurement. Because radar waves are so sensitive to the presence of metals, it's an ideal tool for locating steel, post-tension tendons, pre-stressing tendons in the structure. It does have some depth limits, about 500 to 400 millimeters performance for a system dedicated to scanning concrete. Its depths are also a little bit less precise. So if we're measuring concrete cover with a GPR system versus measuring it with a cover meter, and we set it up as well as we can, we calibrate off a physically measured point, we might be within 1 centimeter uncertainty versus the 1 millimeter uncertainty of a cover meter. The one where things become more difficult is picking up damage, delamination and honeycombing, cracking and voiding in concrete. It's not very sensitive to air. So if we had a concrete structure with something big like a void former, it's going to be relatively well able to see that on the scan. But very small voiding, lip cracking that doesn't separate a great deal are not going to be directly visible as signals on the scan. They may have some effect upon signal strength, which I'll show you in a second, because that is a technique used to evaluate bridge decks, but it's not as simple as working with basic GPR data. Finally, moisture variance is mentioned as well. This does work, but again, in two ways. If you have very moist environments close by to very dry environments, there will be a marked contrast between the two. It's also possible to measure on a known geometry a radar signal transmission speed and compare that. But this isn't something that you can do just by a scanning method. It's a more involved approach done by a more skilled GPR operator. So the final thing I wanted to talk about was one case where they are looking at deterioration and damage on a concrete structure. And this is, they take large volumes of GPR data, they pick each reinforcing bar, and then they look at the signal strength of that reinforcing bar's signal on the data. This provides a map of areas of deterioration. It's not something which could be achieved by running a scanner over the surface and looking at the image. It requires post-processing and a skilled operator, but it is a possible method to be used to look at those bridge decks. I'm now going to move a little bit into electrochemical methods. So these are typically used in looking at the rate or the presence of corrosion of reinforcing steel in a concrete structure. Resistivity is also extremely important for input to cathodic protection design. The resistivity is the inverse of conductivity. The more conductive the concrete substrate, the more quickly corrosion can occur. It's typically measured using either in situ measurement using a Wenner probe method, a 4-point resistance probe. Now, it's very important that the surface resistance and the internal resistance of the concrete gets taken into account. In some cases, it might be specified as part of work you do to use a drilled-in method, or it might be that a surface measurement is useful. It's all to do with making sure that there's no additional sources of error because so many things affect the resistivity. If you have the water content, the level of moisture in the air will also affect the measurements. The other method that's used to measure resistivity is bulk resistivity, and this is where a physical sample of the material is placed between two metal plates, the resistance measured, and the calculation made based on that. What resistivity actually is the bulk resistance, so the resistance per unit of material. So it's an important design input to areas such as design for cathodic protection. The performance of repair mortars may be checked at 7 and 28 days to make sure that a low resistivity repair mortar is sitting low and a high resistivity is sitting high. If you are using surface measurements, they are going to be limited to the first 50 mils approximate of the concrete surface. And there are some relationships between corrosion rate corrosion rate occurring in concrete based upon the resistivity measured in that concrete. For potential mapping, they're specifically referring to mapping out what's known as the half-cell potential. They call out an Australian standard here, 2832.5, and they specify a maximum spacing for measurements. And this is a good idea. I'll cover why quickly. So when you take a half-cell potential measurement, you're forming an electrical circuit through between a reference electrode and the steel reinforcing cage. The reference electrode acts like one half of a battery, and there will be a voltage measured between that reference electrode and the reinforcing steel, and this voltage will change based upon the corrosion state of the steel. You can see here that the effect of half-cell potential measurements of a anode does vary with space. So if you move further away, in this case, the half-cell potentials would increase. So you see that's why the spacings between the sensors is so important, because otherwise it might be possible to miss the spacing. Things that could control the spacing is if you have the cover higher, the spacings need to be closer, because there will be a difference in measured half cells with different position. You may also need to decrease the spacing if you have a high resistivity material. So when we take a half-cell potential measurement, we are using it to evaluate the likelihood of corrosion of steel in a concrete structure. It gives no information on the corrosion rate or the physical state of that steel. It is purely regions where corrosion may be occurring and regions where corrosion is not occurring. And the measurements are most useful for chloride-induced corrosion in relatively dry concrete, not saturated or oxygen-starved concrete. It is less effective as an assessment tool for the extent of carbonation-based corrosion. Carbonation-based corrosion tends to be a little more distributed. So corrosion rate measurements are a link to how quickly corrosion is occurring, and they're done using a slightly different setup where there's a separate current applied to the reinforcing steel and then a measurement taken based upon how that changes a half-cell potential. So this tool is used to establish the rate of corrosion. It's also a more useful tool in some of those difficult cases where you've got wetter concrete or situations where half-cell potential is less useful a tool to scope out regions of corrosion. Moving on from the corrosion investigation tools, I'm now going to start talking about sonic testing tools. Sonic testing tools are most sensitive to the voids and damage in concrete. So where we use a ultrasonic pulse velocity test or an impact echo test, these are the better tools for finding voiding or damage, and also some cases for things like measurement of thicknesses. So the UPV test is called out as suitable for compressor strengths, comparative assessments for qualities, and also as a tool for location of voids, delamination, and undercompacted concrete. We're also given an ASTM standard in this case. The ASTM standard defines a ultrasonic pulse velocity as the velocity measured of the longitudinal stress waves. So the transducers apply that stress wave and receive it at the other end of the structure, and they calculate the velocity that this travelled at. They provide also, the standard also provides the reporting procedure and essentially what the test is and how to collect this data. It doesn't provide much information on assessing the results, but mainly how to collect useful data and a very clear definition of what the test is. So if we're using if we wanted to locate defects using ultrasonic pulse velocity, we need to have the signal path of those compression waves travel through the area of concern. So if the void is in the middle of a beam, they need to be placed on either side of that beam. And depending upon whether we have voiding or delamination or honeycombing, there's going to be slightly different results in terms of that signal. This is where we bring interpretation into the measurement. The other area they did mention that ultrasonic pulse velocity could be used for is compressive strength. And similar to something like a Schmidt hammer, this is not a direct measurement, it's a correlated measurement of compressive strength. So the literature has some relationships they've built using overseas compression tests, where they've tested with ultrasonic pulse velocity before crushing and formed a relationship. There's also a method of using Schmidt hammer and ultrasonic pulse velocity tests together to get a better strength measurement. The quality of your measurements using something like a correlated method is going to be based upon how much setup is done. So if, as a testing company, you go and build your own curves off local samples, ideally of the same concrete mix as used on site, there's going to be a much better relationship than if you're using European standards with no adjustment whatsoever and trying to get that information. But there's a real clear link between the strength, concrete mix, and then the UPV. Once you adjust one of them, it becomes less certain, less useful. So if we're using compressive UPV on site, as we were discussing, it's quite a good tool for voids and delamination. Quality, in terms of how dense and sort of how well compacted the concrete and that is, it's a useful measure there. Compressive strengths, it's okay at if you set it up correctly. But if you are trying to find areas where the strength may have dropped, if you've got something like a concrete pour where you've got some worries about truck number 3, then it would be quite a good measure of relative strength, comparing one area to the other. Impact echo is another sonic test. The big advantage of this one is it's carried out from one side of the structure. So it can be used to assess the thickness and delamination, voiding large cracks. It also gives an ASTM standard. So we'll start with the standard again. The ASTM standard defines impact echo measurement of concrete elements for thickness. It doesn't go into its use for void detection. And it gives 2 procedures. The first procedure is a setup, where it is used to evaluate an approximate pulse velocity of the compression wave from the impact. And then this is then used as input into procedure B, where the thicknesses are actually measured. So it's a useful description of what the test is and its use in thickness measurement, but again, it doesn't go much into evaluating defects with it. Impact echo, the way that it operates is if you strike the surface of the concrete, there will be a resonance established in that concrete, and that resonance for a bulk concrete with no change corresponds to its thickness. The technique takes a sound waveform, it transforms it into frequencies, and the dominant frequency is going to be the resonant frequency of that concrete element, and that's going to match up to thickness. Similarly, if there is a void, that resonance is going to change. So if we are scanning along a slab with an impact echo tool, taking measurements every 200 mils, and we're getting a reliable frequency which converts to a thickness of 120 millimeters, and then we see a change from that 120 millimeters to a higher or lower value, that could be a sign that we're over a defect, or a change in the thickness. So analysing data, typically where you've got a plate-like plain section of concrete with no damage, it will have one clear peak. You may find that multiple layers or more complex environments are going to produce multiple peaks. And finally, if you've got some really rough, bad quality concrete, there may be no dominant frequency in that information. So, impact echo is a very good tool for thickness. The quality of the thickness measurement is dependent upon setting up the speed of sound. So this could be measured with ultrasonic pulse velocity or using the ASTM method. It's a useful tool for finding delamination, especially where the delamination has separated two sections of concrete, the thickness will change markedly on the measurement. Cracking, it's okay at. It's quite useful for finding large areas of cracking, heavy cracking through a structure. It's also good at finding cracks that are perpendicular to the face of the concrete, so more like a delamination or angular crack. If the crack is parallel to the surface of the concrete, I do apologise. So it's a useful tool, but needs to be applied with care for cracking. Voids it's quite good at, but they need to be relatively large voids. So something the size of a marble is probably not going to be seen by the test unless it's directly under the test point. But it's going to be quite sensitive to large areas of band consolidation around the reinforcing steel or similar, so things like honeycombing and such. Infrared thermography is another test called out for void location, and also a location tool. And we're given an ASTM standard. The ASTM standard is specifically for a methodology to assess bridge decks or roads, concrete roads, where they are using video. So this is a video technique, recording a video of the area being measured and a thermal energy video area of the area under test. So looking at both of these, it's possible to remove the influence of surface changes. So if you had a asphalt repair or something over a section of concrete, that would have a different heat. But because you've got video, you can subtract that from the final defect analysis. And then there should be different temperatures in different areas. The standard also specifies that there needs to be direct sun to create some thermal energy and some different sort of retention of that thermal energy. So the output ends up looking like this. It's quite a good tool for delamination. With all these techniques, it needs to be close enough to the surface that the heat can penetrate and affect the top surface. So if you had a very large structure, you would be only measuring so far into it. Now, locating embedments is a little bit more difficult. Again, it requires them to be close enough to the surface to have their position visible and changing the surface heat. Maybe another tool might be easier to use, but there could certainly, if this scan was being taken, could be information visible in it. Now, radiographic testing refers specifically to X-raying of concrete. Sometimes ground-penetrating radar is referred to as concrete X-ray, but it's not. There is actually a physical method of taking an X-ray of the concrete structure. It's very good. It's photographic, so some of the bits of information we don't normally get, we can take with an X-ray, physical bar diameters and such like that. But it's very slow, especially for large structures. It can take a long time for the X-rays to penetrate with enough energy to activate the receiver or the photographic plate. And it's also a real pain for access because the entire area nearby needs to be cleared because there is the radiation involved with the test. So it's very useful for finding the steel, again, and then it's going to come down to operator skill in locating other tools. Cover thickness and density of concrete I want to call out specifically because both of these would require relating the speed of the X-ray transmission to the results. So this is a little more difficult. This is, again, a skill task. It's not one you would send out with a normal X-ray company. So finally, I'm going to talk about Schmidt-Hammer testing. Schmidt-Hammers are mentioned as a reason of locating areas of poor concrete and variability in concrete strength. They also provide a ASTM specification for the test method. So the ASTM specifies the determination of a rebound number, and so its main information is how to collect Schmidt-Hammer data and how to use that to come up with a final value of the rebound number. If you want to convert that back to strength, that's a different task again. The standard defines the method of test, not so much the use of the data. So Schmidt-Hammers operate by placing a metallic plunger against the surface of the concrete. A mass is spring-loaded onto the back of that plunger and rebounds a certain height. Then either the rebound height or the rebound speeds are measured and converted to that rebound number. So that could be an R value or a Q value. If you're looking for consistency or regions of poor concrete, you can go straight with the rebound value. If you're looking for compressive strength, we need to use a conversion curve again, just like with the ultrasonic pulse velocity measurements. So if you make your own curve, it's going to perform better. If you're using what's known as a lowest 10 percentile curve, where 90% of the data points collected are allowed to sit above the graph, like the one on the right shown there, you can see that it's going to be conservative. It's going to come up with a strength that sort of can be thought of as this strong or stronger. These are so if you're using Schmidt Hamilton compressive strength, it's important to understand it's a useful tool, but it's not incredibly precise on exact strengths unless you calibrate. But it is very good for finding variance in concrete strength and regions of poor concrete. One caveat on the poor concrete is it's a surface test, so it's going to look at the first surface areas. It's not going to look at the whole extent of that concrete. This is the end of the formal presentation, so I'd be very happy to answer any questions you have in the live chat or go through any other topics that would interest you. Hello everyone. Do we have any questions? I'm going to watch the live chat. It may take a few seconds for your question to reach me because there's a slight delay from when I broadcast to when it makes it onto the live chat. Okay, so the bar diameter technique that people will sometimes attempt relies upon a very good calibration of the GPR for radar velocity. When we want to know depths with GPR, we first need to look at what radar speed is transmitted at. So if we have a known element on that structure, such as a 150 mm measured wall, we could scan it with GPR, get the depth appearing on the image from that scan to be very clear. 1 second, I'll bring up a GPR scan. So with that GPR scan where we saw the depths measured here, we would make that measurement very precise, and then we're going to take into account that reinforcing bars usually sit one on top of the other. So we'll look at the measurement here to here, so top surface to the top reinforcing. Then we're going to scan at 90 degrees along the surface of the concrete, and we're going to look at reinforcing in the other direction, and we're going to look at measuring the depth of that second bar, which should be in contact with the first. So the difference for the steel on top should be an estimate of the reinforcing diameter. As you can see, it's not really an ideal measurement, but it is something that can be used. Look, thank you very much for the question, Yusak. Hamid, thank you very much for the question. If you're not watching the live chat, the question was how certain the corrosion detection is for reinforcing. So this does depend upon correctly collecting the data and interpreting it. There's a fairly involved process in working with half-cell potential data. Firstly, the survey spaces need to be chosen and a map of the data formed. 1 second, I'll try and pull up an image for this one too. Okay, so if we look at a physical layout where we've color-coded regions of different half-cell potentials, we can look for a couple of different approaches to locate areas of corroding reinforcement. We can try and find hotspots where the corrosion potential changes markedly to the corrosion over the rest of the structure. Or we can actually do some statistical analysis upon large data sets. It's possible to look at the distribution of half-cell potential voltage value for the whole structure and pick out those that are likely due to non-corroding reinforcement where a measurement's been taken, and also to measure regions where the I beg your pardon, to measure regions where the reinforcing is corrosion. These two numeric values, the distribution of them can be used to statistically